So is everybody excited about Longhorn? Yeah? Excited about Whidbey? C++? Yeah, very nice. C++ in Whidbey, and even before Whidbey, provides the best interop scenario for integrating managed code and .NET APIs into your existing C++ code. We're the only language that provides the level of power and flexibility that most developers require for the types of complex solutions that they develop every day. Leveraging the WinFX APIs in real-world applications will also most likely require the use of these technologies in order to get real solutions implemented. The subject of this talk will cover some of the practical aspects of bringing native code forward to use .NET APIs and some of the solutions that we provide in Whidbey to solve problems that we've had with previous releases of the tool sets. My name is Scott Currie. I'm a program manager for the Microsoft Visual C++ team. I primarily work on the back end in the code generator on these interop technologies, managed code generation, and the 64-bit compilers. If you have questions about any of those, feel free to ask them at the end of the session, in email to me, or in the product pavilion at the booth. Today's agenda will first start off with the 4 basic ways you can do .NET and native interop. I'll go quickly through the 3 that really aren't nearly as interesting, and then drill down into C++ interop, specifically discussing the new compilation modes that we're introducing in Whidbey and the role that they play in a complex solution, discussing the details of how the interop actually works and some of the performance costs that you have to be aware of and some of the performance solutions that you may have to implement. We'll discuss the CLR calling convention, which will be important for a variety of user scenarios. Mixed DLL loading. Who's familiar with the mixed DLL loading problem? Everybody out here? Very nice. Let me give somebody a t-shirt. I don't have a very good arm, so people who are sitting up front get better access to swag. Mixed DLL loading problem in Whidbey is solved with no workarounds required by the user. Hope everyone's excited about that. The ability to delay load the CLR will also be key for several managed native integration paths where you don't necessarily want the CLR coming in when you first load up a mixed process. And finally, we'll discuss the role application domains may play in the future and some of the solutions that we have for making sure that your code is correct in the presence of multiple application domains. So the first way to do native and .NET interop is to use COM interop. Now, COM interop can work in both directions, though slightly different mechanisms work for each direction. The first one is if you need to make calls from .NET into existing COM objects. And to do that, you create a .NET wrapper for your COM code, and it's what's called a runtime callable wrapper. You create one of these either using the tlbimp.exe tool that's distributed with the SDK, or you can create them using an interface that Visual Studio provides. There's a references tab that you can use to import registered COM objects, and it will automatically do the tlbimp call for you. The other way you can go, if you need to call from your existing COM code into .NET, you can create a COM wrapper for that .NET, and that's what's called a COM callable wrapper. Those wrappers are generated using tlbexp.exe, also shipped with the SDK, and again, Visual Studio provides a convenient interface for doing this. All the type marshalling that's required is handled by the CLR. Keep in mind that this type marshalling can be expensive, and you really don't have a choice about where the marshalling happens. Wherever your com.net boundary is where your marshalling happens, where your transitions happen, and if those happen to be chatty interfaces, you have to pay a large performance penalty, and you have no control over that. Another downside is that the TLB imp tool, for example, and also the TLBX tool, creates code that you have to maintain. You'll get an assembly in the case of TLBimp, for example, an interop assembly that you'll have to deploy in order for your solutions to work, and also that you'll have to keep up to date if you happen to make changes. This solution is very useful if you've got a simple interop scenario and you have a lot of existing COM interfaces that you need to bring in. The second way to go, well, actually I'll give you a demo of how this works. How many people are familiar with the COM interop story? Actually less than half, so I think this demo will be useful. So bringing up the IDE, I've already created a COM project. There are some things in here that if I go through every single step, we're not going to have enough time for all the content we want to cover. But I've got a COM implementation here with a method I expose called Fibonacci, and all it does is compute the nth item in the Fibonacci sequence. Fibonacci sequence, is everyone familiar with that? Each number is equal to the sum of the previous two numbers in the sequence, with the first two numbers being 1. We've also got a consumer here that wants to consume just a managed DLL, which exposes that COM interface and makes a call into the appropriate function. So you'll notice here, if you look closely, that this is the new syntax for C++. So someone go ahead and point out a nice, interesting feature of this. The pound using of mscorelib.dll, gone. Oh, I'm sorry. Thank you. Just 1 second. So let's bump this up to about a size 22. That should be big enough. Unfortunately, with this particular version that I've got installed, I'm going to have to do a restart in order to get that to load up properly. So with the new syntax, we've got no pound using of mscorelib.dll, and all we have to do is do a pound using of the interop DLL that we've created using tlbimp, and instantiate the class, call the member method, and then we can start using it. The up arrow is interesting. This is what's called a managed handle. It's a handle into the GC heap. It does not work like a pointer in that you can't do arithmetic on it, but it does allow you to very easily track what types of objects you've got on the GC heap and what types of objects that are not on the GC heap and that you can access directly through memory. This t-shirt, by the way, that I'm giving out, some of you may have seen it at the Product Pavilion booth. It says, "Can you handle C++?" It's using the handle operator there. So some puns there. So if you run this, everything really works as expected. Yes? Yeah, actually that's a bug. Should be GC new. Thanks for catching the bug. So this runs successfully, prints out the first 20 Fibonacci numbers. And all I had to do in order to create that TLBimp wrapper is run this tool TLBimp, which is TLBimp on the XE, specifying as input the DLL, and it gives me a specifying the TLB file, and it gives me the output DLL. So COM interop for simple solutions like this is actually relatively straightforward and works pretty well. The next main way to do managed native interop is to use DLL import. Now this only works in one direction, when you're trying to make .NET calls into machine code. And the way you do it is by specifying an attribute on the method declaration that you want to import. And then that'll import whatever DLL you've specified in the attribute, pull out the function, and it'll do marshalling according to how you've actually done your declaration. This is very useful if you've got existing code which is exposing your APIs through DLL exports. And I'll show you an example of how this works. So again, we're going to go with the same code, so we've got some level of continuity. There we go. So we've got some level of continuity. First, we're doing a DLL export on Fibonacci. We do a definition of it, same code as before, except we have to use the extern C here for DLL import to work appropriately, which is a downside. For consumer.cpp, we do a DLL import on Fibonacci.dll. Since we're not specifying a name there, it uses whatever name I'm using in my declaration here. So it's the Fibonacci function with int n. I consume it here, as before, just doing a direct call to it now that I've done the DLL import. And this works as well. I've got a separate DLL which gets loaded, and it loads up all the Fibonacci numbers. This is a bit of a bug in the debugger in that you have to keep hitting F5. This is all early release stuff, as you'll see when you install the bits on your DVD in the bag. So the third major way of doing it is CLR hosting. And this works only in the direction of native calls to .NET code. What you'll use in order to do this is the ICLR runtime host API, which is provided in mscore.ee.h. Has anybody used the iCore runtime host to do CLR hosting in the past? So, few people. It's about what I expected. We've got a new version of the interface, ICLR runtime host, which adds some additional functionality, and I'll actually discuss some of that functionality a little later on in the talk. In order for this to work, the native application has to drive all of the managed execution, from loading the CLR into process, setting up an invocation context, and actually calling methods. This really isn't recommended for most users. For the majority of scenarios where users have to call from native code into .NET code, there are better solutions available, which I'll discuss next. I'll give a quick demo of this, though, in case folks haven't seen it before. Let them know a little bit about what this looks like and get a taste of some of the complexity involved here just to do a simple call. So what I've done is set up a managed project with just one file, and all it does here is have the Fibonacci function again, and this time just to emphasize that it's managed. I've got a class which calls the Fibonacci function for 25 and then shows that in the message box. So if I go to the simple CLR host, this is what you have to do in order to get it to work. First, you have to set up your ICLR runtime host. You need to bind to a runtime to bring that all into process, and here's what the argument list looks like for that. You have to provide all the information about exactly what you want, essentially. Going further down, you have to get your app domain. You have to set up an invocation context. Continuing down, you have to locate the class that you want to call into and the assembly that you want to call into. And then finally, you get to do your invoke. So there's quite a bit of code here that really only does this. Of course, this sets up a lot of, you had a scripting scenario, for example, where you want to have a native application where you script it with managed code. This can often work out pretty well, where you write your scripting host using the hosting APIs, and then they'll plug into the hosting APIs. When you write scripts, you'll write them as managed DLLs, and they'll plug in that way. But for most users, this doesn't make a lot of sense, so I think we'll just move on to the next, and the best interop solution, which is using the C++ CLR interop features. This is by far the most flexible of any of the solutions. It allows you to take, for one thing, call in both directions. You can take your .NET calls and add them directly to your existing C++ code. You can have any of your existing C++ code, call that directly from any new managed code that you're writing. And you can call any of your existing C++ code through a .NET wrapper class. So if you want to expose your existing C++ code to other languages, it's very easy to do that by creating a wrapper which goes around that existing C++ code and exposes that functionality to, let's say, C# in a CLI compliant way. In order to get this to work, all you have to do to get started is to compile the appropriate source file, whatever needs to have the interop functionality, with the /CLR switch. And one of the big benefits of this is without adding any additional binaries, you can continue to call all of your existing code that you have compiled /CLR from other native code that doesn't know anything about the existence of managed code. The flexibility comes in from the fact that when you have these mixed assemblies that we create, they can either call managed or native, and they can be called from managed or native. It's completely transparent. And as a result of this, it's useful for almost all user scenarios. So I'm going to give actually a couple of demos here. The first is going to follow the same pattern as the Fibonacci demos we've been seeing so far. And the second one takes a real-world application and makes things a little more interesting. So with the Fibonacci stuff we've been seeing so far, we've got what we expect to see, Fibonacci.cpp, which is just a function, no extern Cs, nothing like that, just the implementation. I've got a simple declaration in the header, exactly like you'd expect to see. Now I could put this in the separate DLL, but I have the flexibility with this solution to integrate it all into the same assembly, all into the same executable. All I have to do is pound include Fibonacci.h and directly use the functionality from within this code and directly pass it along to my managed APIs. So if I hit F5 here, everything works as you expect it to. And I didn't have to do anything except add my managed API call. So this actually doesn't do the C++ interop functionality much justice because it's such a simple example. Has anyone here seen the Quake 2 demo? Just a few people, about maybe 25% of you. So I'm going to show a slightly expanded version that you may have not seen. So Quake 2 is an application that was released by id Software quite some time ago. It's a first-person shooter game. I hope folks have a bit familiar with it. What we've done is ask Vertigo Software to take the Quake 2 source base, which was released into open source by id Software about a year and a half ago, and recompile it using the /CLR interop functionality. And then from there, do some extensions. But what I first want to do is show you what some of the performance impact looks like. So this is actually the native version of Quake 2. And what I'm going to do is run time demo on it, which is a bit of functionality that they provide for benchmarking systems using this software. Now this is just going to go maximum speed, collect a bit of data, and once I've got a sufficient sample, I see that I've got about 35.2 frames per second. So let's remember that number. Because then when we go into our CLR implementation, and I'm going to have to drop the resolution down here because the other one was 640 by 480 and this is 800 by 600. That's not a fair comparison. IJW is great, but it's not that great. Let's drop that to 640 by 480. And then do the same thing. Time demo 1, and let it run. Looks like it's keeping up pretty well. 35.7 frames per second. Actually, in this case, slightly faster. That's not what we always see. Depending on the particular processor, we see a bit of a difference. On this particular processor, which is a P3 kind of early model, they run about at parity. If you're running on a very modern P4, so pretty much the worst case scenario for IJW, since the static compiler does a very good job of optimizing for that particular processor core, you're going to see about a 15% difference. That's 1.5. Now, in exchange for paying this 0 to 15% difference in performance, you get a lot of very interesting functionality. And here's the functionality that the Vertigo team decided to add. Well, first you'll see in the upper left-hand corner of the box, we've got built with Microsoft Visual C++.NET, running on the .NET Framework, version 1.1, ported by Vertigo Software Incorporated. That's rendered using managed code. Those are the .NET drawing APIs that are rendering right on top of the actual game screen. But it gets a little cooler. If I start up a game, and then I invoke what they've termed the radar API by just typing in radar here in the command console, I get a WinForm, which provides radar for the game. So the center here is where I'm located. Everything blue are objects, everything red are enemies, and everything green is a power-up. And what's even nicer than that is that I can overlay this directly onto the render screen. There we go. And it updates real time. So I paid from a 0 to 15% performance hit to get the functionality where I can start using the managed drawing APIs directly and actually even overlay them on top of the render screen. Now keep in mind what's involved in being able to create a radar module like this. It has to go into the game engine and discover the location of every single one of these objects, collate all that information, and then render it onto the screen. That's a very high-touch scenario, especially since Quake 2 wasn't architected with the interfaces in mind to make these things really easy. So this is something that really couldn't be done in COM interop, for example, without re-architecting the solution. With Visual C++, it's easy. This took them a couple of days to do. So this really demonstrates in a real-world application some of the power of the C++ interop technologies. Now that we see the power, we're going to drill down a little bit more into some of the facilities we provide newly in Whidbey and some of the existing facilities in order to make this transition easier for you. So the first thing I'd like to discuss is compilation modes. We've added 2 new compilation modes, and they can be very powerful for your new code scenarios. The new code that you're building on top of your existing code. So an important concept to understand when you're talking about interop scenarios is the difference between code and data. You can have both unmanaged code and unmanaged data, And you can also have managed code and managed data. You can have scenarios where MSIL code, this is your CLR code, is talking directly to native data that's sitting on the native heap. Just because it's MSIL doesn't mean that it has to talk to CLR data. So we're all familiar with the scenario of native C++, where you've got native machine code and native data types. Anyone who's used the previous interop technologies in Visual Studio 2002 and 2003 will also be familiar with mixed C++ / CLR. And that's what you're going to use for the majority of your interop scenarios. We've also added CLR Pure. Now this is useful for those portions of your application that you can get to compile pure, meaning that you don't do a lot of comment. So if you've just got some simple functionality, maybe you're doing DLL exports that you could turn off for particular pieces, you can recompile to CLR Pure, which will eliminate all native code from the image, make the image CLI compliant, and it opens up the door for a lot of tools-based scenarios. So if you've got some portion of your application, or maybe a tool that ships along with your application that you want to use with click once deployment, CLR Pure would be the way to go. Also, if you're doing any reflection on your code with tools that use reflection, CLR Pure is necessary for those scenarios. But for your primary, bringing the legacy code forward, you're going to be using mixed C++. The final compilation mode we've added is verifiable C++, or CLR Safe. Has anybody tried to use the 2002 or 2003 tool sets to create verifiable images? Yeah? You deserve a t-shirt. It is, let's see if I can reach you. They don't carry very well. My arm's not that bad. The user model is quite frankly terrible. You have to jump through a lot of hoops to get things working. If anyone has questions about how bad it was, they can ask me or this fellow over here. But in Visual Studio 2000, in the Whidbey release, we are going to have a /CLR safe compilation mode where all you have to do is throw the compiler switch. If you're doing anything that's unverifiable, you get an error from the compiler, tells you exactly which line number to go to. You go to the line number, you fix it, and if you're getting a build without errors, you're getting a verifiable image out. Very nifty. So since we discussed the compilation modes, by the way, you'll use the safe stuff for any parts of your application that you want to start being able to leverage some of the safe functionality with. So if you've got some code that you want to share perhaps with a stored procedure that's eventually going to sit inside of Yukon, it'd be a good idea to make sure that that compiles safe. So next, let's dive into some of the interop details. And this is where we get into the really meaty, interesting part of the interop and some of the performance issues that you might run into. So this is what's often referred to as the magic of interop, or using our old name for the technology, the magic of IJW. The way we get all this to be wired up appropriately is that all of our global or native member methods have both unmanaged and managed entry points. So I just read it off the slide because it's very important. For every single method, you can either go in through an unmanaged entry point or an entry point, or a managed entry point. So you can call from either unmanaged or managed code. Now the way we get this to work is that we have one of those entry points be the method implementation. That'll contain the code that actually performs the logic that you've defined in that method in the source code. The other entry point will just be a forwarding thunk, which forwards over to that method. Now the method implementation is almost always MSIL. The only cases where it's not is if you happen to have, one, done something where we can't generate it. And these include things like having inline assembly. We can't always convert inline assembly over to IL appropriately, so we don't even really try to. It's a hard problem and doesn't have a lot of benefits. So if you have an inline ASM block, you're going to have an unmanaged implementation. Or if you're using some intrinsics that are CPU specific. For example, if you're taking advantage of some of the SSE intrinsics that we provide, those obviously aren't going to map very well over at MSIL, so we generate the native code for those. Also, you have the ability to specify that you want the implementation to be in native code. So if you've done some aggressive hand tuning of a particular implementation of a method, all you have to do is put a #pragma unmanaged around it, and then you have the ability to maintain the performance that you've worked really hard to get from that native code. So for your really performance-sensitive pieces and code paths of your application, you've got that option, and we provide it through the #pragma unmanaged compiler directive. But there are some consequences of having these two entry points for the function. At many points in the compilation, you'll have to know statically which one you actually want. And two really good examples of this are if you have function pointers and you want to assign that function pointer to some function that you've got, which is compiled /CLR, or if you've got a virtual call and you need to fill in the vtable slot. You can only fill in that function pointer once. You can only fill in that vtable slot once. So you have to choose one or the other statically. And for compatibility, and that's the compatibility of unmanaged code being able to still call into these methods, we always choose the unmanaged entry point. But this creates a problem if you've actually got a managed rather than an unmanaged caller, which is what we call the double p-invoke problem, or sometimes the double thunk problem. And here's an illustration of it. I have a managed caller, and this calls through a p-invoke, through an IJW thunk, essentially, into the native entry point, which I put into my vtable slot or into my function pointer for compatibility. All this is, it's a thunk to the actual MSIL method implementation. So it just thunks right back into the managed target. What we actually wanted to do was a direct call from the managed caller to the managed target, but we had to take this loop in order to get there for compatibility purposes. Now, notice that we've crossed the p-invoke boundary twice. Anyone who's done a significant amount of interop knows that p-invokes are very expensive. So if every time you're making a virtual or an indirect call, you have to pay for 2 p-invokes, in addition to the regular indirections that you normally have to do with your indirect calls, you've actually found yourself in quite a bit of trouble. So this is a major problem. Has anyone run into the double p-invoke problem? Very poor virtual call or indirect call performance? You're pretty far out there. Come see me later. This t-shirt's for you. So there are a couple of possible solutions to the double p-invoke problem. We're actually investigating all of these. The first one, which I didn't list on the slide, which is kind of almost the obvious solution, is make p-invokes faster. If p-invokes were a whole lot faster, if they were really fast, you wouldn't care if you were doing 2 of them so much. But it might be difficult to get them quite that fast. So what we're looking at are other possible solutions. The first solution is to use CLR Pure. CLR Pure removes all the native code constructs, so you don't even have that native entry point anymore. You know you're not going to have a native caller, so you can just go ahead and fill in your vtable slots and your function pointers with the managed entry point, and you're safe, and then you just get to do a direct call. The second way you can do it is to use the new CLR call keyword that we're adding. I'll discuss CLR call a little bit later, but for now you can just think of it as a directive that will allow you to put CLR Pure on a method-by-method basis. So on a single method I can say, this is never going to be called from unmanaged code. Don't bother emitting the unmanaged entry point. And when you do that, there's no longer one of these overload conflicts, and you can just fill in your function pointer and your vtable slot with the managed entry point. The third way to get around this in Whidbey, and this hasn't been finalized yet, this actually might not happen, but we're going to have a solution that fixes it, and it's most likely going to be this one, is that you do nothing. And this is what's called the auto double p-invoke elimination. What happens is that the compiler emits those thunks that you saw that were in native space with a cookie in them. And the cookie starts off with an instruction that just jumps to where the thunk was originally going to start, and that's for compatibility. So if you actually call in from a native caller, you just do that jump and then go off on your merry way. And then after that jump, we've got some additional stuff. We've got an invalid opcode, which is going to say pretty much that this isn't valid code that any user is trying to generate. Then we've got this magic cookie, and this cookie is just a number that we look for, and you'll see how we look for it in just a second. And then the fourth instruction contains the address, or on some platforms, the token of the managed entry point that we actually want to call into. So what happens is that the runtime is going to look for this cookie. But if you're an old runtime, you're not looking for the cookie, it doesn't matter because it's fully compatible. You can still do that jump through and it all works. If you're a new runtime, you check for the cookie, you see the existence of this invalid opcode and this magic number, and then you just check the next D word here, you get the managed entry point that you actually want to call into, and you do a direct jump without ever having P invoked. So let's see how this adds to the illustration. We've got our original problem, and then when we add the automatic double thunk elimination, what happens is this runtime generated managed P invoke, the one that happens before we cross the P invoke boundary, accesses this compiler thunk, finds this cookie, accesses the managed entry point, and does a direct jump. So it's actually a pretty complicated, and you might call it a hacky solution. And that's true. But we're putting a lot of thought into these p invokes, and everybody else should be putting thought into these p invokes, whether or not you've actually run into this problem before. Because, as the moral of the story is here, p invokes are expensive. They're so expensive that we invested all the hours that were necessary to come up with those various solutions. So you have to think about the cost of these transition thunks when you're constructing interop solutions. Specifically, you need to design solutions so that you don't put your interop interface at the chattiest part possible. You need to be careful so that you're moving it around so that you're not doing a lot of p invokes and a lot of marshalling. And I'll show you kind of an exaggerated example here of the havoc that chatty interfaces can wreak on your performance. So we drop into this demo for chatty interfaces, and we bring it up here. We've got two separate implementations that are very similar. You've got some native code, and the native code is identical in both cases. I've got a var args function average. It could just as well be printf. And all it does is take count number of arguments off of the VA list, add them together, and return an average. It's the same in the chatty side. So if you look at the chatty implementation of this, I'm going to execute everything 5 million times. Right? I've got this function main, which just does the average and then prints the result. And what I do is for 5 million iterations, I just average these 7 numbers. Now what's happening here is I've got a main function. Since I'm compiling this file /CLR, and I'm not compiling native.cpp/CLR, the main function is compiled into MSIL. It has a native entry point, but the actual method implementation is MSIL. This function right here, which actually calls the average code, is compiled into MSIL. Again, it has a native entry point, but the actual logic there is an MSIL. And then we're calling into this native function average. So what's happening is that 5 million times, I'm having to do a p invoke here. And one of the reasons those p invokes are so expensive, especially in the case where you've got a lot of arguments to your function, is that the calling convention for managed and native code are different. One big difference is that your arguments are in reverse order. So if you're calling from managed to native, you need to take every argument off the stack, swap it around, and then do your call. And the same thing when you go back. So if we call chatty here, I'm going to do a build. And I've got a tool here. It's just a timer. I'm going to call ltimer on this chatty interface. And it'll just run it and spit out the time at the end. So it took 5 seconds to run 500,000 iterations. And here was the result that it printed out. It printed out 0. So now, if I go to chatty, what I've done is added a pound pragma unmanaged around the average. So what we're doing here is saying main is going to be implemented in MSIL, but this function that main calls just once is implemented in native code. And then this average function that we call 500,000 times is also implemented in native code. So we're doing our p invoke once from main to count spaces rather than 500,000 times from count spaces to average. And the result of this is quite dramatic. Takes less than a second. So we're looking at about 5x. Now this is an exaggerated example, obviously. You're probably not going to see a pattern that looks exactly like this in your code. But you're also probably going to be happy with improving your code performance by less than 5x. 20%, 30% could be a big win. So what you have to do is keep an eye on where some of these interfaces end up being if you're seeing a big slowdown when you start moving over to the C++ interop technologies. And look for this as one of the main potential culprits. And normally the solution is just going further up or further down the chain for where you put your interop point to a less chatty part of your managed native interface. So next up is the CLR calling convention. CLR calling convention actually has quite a few uses. We've added the CLR call keyword to the language. It's very similar to the cdecal or std call keywords. It's a calling convention specifier. It can be used in several ways. The first way is as a modifier to a function. And what this says is there will be no unmanaged entry point for this function. So as a result of that, you're not going to be able to call this function directly from native code. You will still be able to call it from interop code, from IJW code that's got the MSIL implementation, but you can't actually call it from the native code since you don't have the unmanaged entry point anymore. This will also cause the compiler to use the managed vtable fixup on virtual functions, and it will cause it to use, obviously, the managed entry point when it's filling in the entry point for indirect calls. You can also use it as a modifier to a function pointer, and you would do it in much the same way that you would use cdecl or studcall, except it has the additional use of being able to specify which overload to take. So for example, if I want to do an indirect call on a function that's been compiled with the interop technologies, which has both the managed and the unmanaged interfaces, if I leave the compiler to its own devices, it will just take the unmanaged interface to assign the function pointer. If I say that this is a CLR call function pointer, it will instead take the managed entry point. So just by adding this calling convention specifier to my function pointer declaration, I can totally eliminate, without even having to go into that CLR generated thunk, which will check the cookie, I can remove even all the cookie checking time just by adding the CLR call calling convention specifier to my function pointer declaration and calling through that. Also, we've added a new use for all of our calling convention specifiers. It's called declspec calling convention. You can use it with CLR call. You can also use it with studcall and cdecl. And you can put this on an entire type. And what that will say if you put this on your type is that all the methods which are exposed by this type will use the calling convention that you specify in the declspec. So what we've done here essentially is allow you quite a bit of granularity in the degree to which you choose to convert all of your APIs over to managed only if that happens to be the right solution for you. You can do it on a per function basis by using the CLR call keyword. You can do it on a per function pointer basis by using the CLR call keyword. You can do it on a per type basis using our new declspec, or you can do it on an entire source file by using the /CLR pure compiler switch. There are several uses for this. First, as I mentioned before, you get your penalty-free virtual and indirect calls. There will be a slight penalty to whatever auto double thunk elimination solution that we do have. It's going to help the problem quite a bit, but it won't be a 100% speed up to native code-like performance. And this will be pretty much as close to the native as you can get on those virtual calls. You also have the ability to specify the CLR pure on individual types or individual methods, as I just mentioned. And a very important aspect of this is you get interoperation with your pure implemented functions in a file that you've compiled /CLR pure from a file that you haven't compiled /CLR pure. And I'll give you an example of that in this demo, in addition to an example of the performance speed up that you can often see. So I have to exit out of chatting and go into our CLR call. So the first example here, I've got a file called pure.cpp where I again implement our old friend Fibonacci. And I expose this through a header file and consume it in the CLR call.cpp. And essentially all I do here is in main, I've got some other code which will be the second part of this demo. But in main, I just call Fibonacci and I do a console.readline on the Fibonacci. So if I run this or try and build it, I get an error. Unresolved external. Can't find cdecl Fibonacci.int. It's looking for the unmanaged entry point because it doesn't know anything about that Fibonacci function. And it can't find any entry points because only the managed entry point exists. So what I have to do is go into the declaration of this and specifically say that it is a CLR call function. Now, of course, since this header is included in the CLR call.cpp consumer, it sees the CLR call, and now everything builds successfully and it runs successfully. But before running it, I'm going to show you a different version of this file, which does a very similar thing with respect to this calling of a sum. So I've got this one function here. Now, this isn't using the new managed syntax because this is actually supposed to be a native class. It's class foo, public. It's got a virtual member sum, which just adds 4 numbers together and returns them. I've got something in here that consumes it, again, about 5 million times and just runs it. So here I'm paying the double p invoke penalty. Here in CLR call, I've said that this is a CLR call virtual function. So then when I call it, I'm calling through a managed vtable entry, and everything gets patched up for me in a way that's most performant. So again, if I show you what the performance looks like on the virtual call case, I can run ltimer first on this double thunk. Now keep in mind that this particular version of the toolset doesn't yet have an implementation for our auto double thunk elimination solution. So just this case will be quite a bit better in Whidbey. It's not going to be 5 seconds. It's going to be quite a bit faster than that. But at the same time, oops, that was my fault. Let me run that again. But at the same time, it's not going to be 0.3 seconds. 0.3 seconds versus 5 seconds, absolutely tremendous. It'll probably be in the Whidbey time frame more like 0.3 seconds versus maybe 0.5, 0.6 seconds, for example, like this. But that's still a performance hit that you don't want to have to pay if you don't have to. So that's CLR call. Next is mixed DLL loading. So the mixed DLL loading problem, for those of you who aren't familiar with it, in our Visual Studio 2002 and 2003 products, we generated code where in mixed DLLs, we would be running managed code under the loader lock. This is something you should never do. And I'll just give you a simple scenario for why this is such a bad idea. If you're in the loader lock and you're running managed code, and you happen to reference a type that's in an assembly that hasn't yet been loaded by the runtime will do you the tremendous favor of loading that assembly for you. Now, the way the runtime loads an assembly is the same way that you would load a DLL. It calls load library. What does load library try and do? It attempts to acquire the loader lock. You're already holding the loader lock, and you're now deadlocked. Definitely a bad idea. Now, there are many much more subtle instances where this can crop up, and that's where people tend to get bitten by it most. In fact, depending on the particular parameters of the system, you end up with a race condition that gets triggered non-deterministically. So it's very difficult to diagnose. Most people have never actually been able to repro this under normal conditions, under non-stress conditions, or if they're not signing their assembly, for example. But once you do one of those things, or once perhaps the CLR or the operating system changes in such a way that changes the parameters of the race, all of a sudden this code you've already shipped to your customers could start deadlocking unpredictably. Definitely a bad solution. So that's why we published the loader lock workarounds. They're available on MSDN. If anybody has got code where they're getting a warning out of the linker that says you have to link this no entry and you've ignored it, do not ever do that. Come up and talk to me afterwards if you're doing that, because you need to fix it if you're going to be shipping before we RTM Whidbey. But in the solution essentially is that you link no entry and you have to do some manual initialization of those DLLs. In Whidbey, all you have to do is just rebuild your DLL and it works. If you happen to have done the workaround, no need to remove it. It'll still work with the Whidbey toolset. If you want to remove the workaround or you're writing some new code that would have required the workaround, that's fine too. It'll just build and we'll do the right thing in the toolset. And again, if you ignored the 2003 warning, you have to rebuild your DLL either with Whidbey if you're not shipping for quite some time, or if you're shipping, which is the more likely case, you have to put in the workaround. Please talk to me about that. There's really no demo of this because all it would be is building a DLL and having it work. So I'm just going to move on for the sake of time and show you a pretty cool feature, which is delayed CLR loading. So loading the CLR up front is not a good idea for a lot of reasons. One, you might not be using managed code for quite some time in your application, especially if you're bringing forward some existing C++, and especially if you want to keep some of that existing C++ native. So if you brought in the CLR up front because you've got some managed stuff in there as well, you're talking about the entire working set of the CLR spinning up. You're talking about the performance of having that spin up, which is going to take some time, and your load time is going to suffer considerably in addition to your memory footprint. Additionally, you're going to have a situation where you might want to only be consuming WinFX technologies, and you're not interested in the CLR being present at all in your process unless you're actually using those WinFX technologies. And if people are using a downstream operating system like Windows XP, you don't want the CLR to show up at all. Also, if you're going very far downstream like Windows 2000, they might not even have the CLR installed. And that might be a blocker for running your application. They can still run along your native code paths, but we're requiring you to load the CLR up front, which is a major problem. In Visual Studio .NET 2003, CLR loaded on process startup for any mixed DLL that you had. In Whidbey, we'll take a very small code path through the CLR, only using mscoree.dll, and the remainder of the CLR load is deferred. Currently, mscoree.dll isn't part of the redistributable binaries that we ship with .NET. We're seeing if we can change that for Whidbey. No guarantees yet. But if that was redistributable, that would completely eliminate any of your down-platform concerns. If you wanted to have something that targeted Windows 2000 users with native code that had some specific WinFX API calls in there that you never took when you were running under Windows 2000, all you'd have to do is ship mscoree.dll, which is 150K with your application, and the user would never have to install the CLR if they didn't want to, which is great for a lot of enterprise customers that don't want to change their configuration. So I'm going to give you a demo of this, because it's kind of nifty to watch. So I bring up my delayed.sln, and I define a DLL, and I've just got two very simple functions in it. I've got extern-c, declspec export, I've got manage, it returns 84, and native, it's a function that just returns 42. These could have done more, but there's no reason to clutter the sample. In the exe here, I go through by first printing program started. I load library, the mixed DLL. I say that it's loaded. I get the address of that native function. I execute the native function. I get the address of the managed function. I execute that managed function, and then I quit. So what we should expect to see here, since this is a managed exe here that I'm compiling, is that we don't see anything but mscoree.dll until not we find the entry point, but until we actually execute that function. So let's see what happens. Hit F5. I get program started. Now here behind me in my debugger window, I've opened up modules so I can see everything that's loaded up. So when I actually load my mixed DLL, I see that mscoree.dll does come in the process, but there are no other CLR DLLs here. I then go through, find my native entry point. The DLL list hasn't changed. I execute the native entry point. DLL list still hasn't changed. I find the managed entry point, no changes, and then I execute, and wham. See how far that scroll bar went down now? That's everything that the CLR pulls in the process. I've got mscore works, which is several meg. I've got mscore lib, which is several meg. I've got mscore jit, which is several meg. Also some other DLLs that I didn't have in process before, like comcuttle32. All gets pulled in. But of course, that didn't happen until I actually executed managed code. So this is a great deployment story for folks who are looking at incrementally building WinFX technologies into their product, but not having to affect any of their customers who haven't yet upgraded to Longhorn. So the last thing we'll be talking about is application domains. Application domains can be thought of as kind of like a managed process that exists within a process. You can have as many of them as you want to within that single process. They can be independently started or stopped. You can't directly access the code or data of one app domain from another app domain without using a remoting API, which actually looks a lot like inter-process communication. You can have your configuration information scoped per app domain. You can load your assemblies in multiple app domains. They really are kind of like process concepts. They're independent concepts for the managed world. Currently, these are used extensively in ASP.NET. Every ASPX page will be loaded up into a separate application domain. And this is the best example we have of a currently shipping product where application domains are being extensively used. They'll be used more and more as time goes on, and applications are architected from the ground up to be managed friendly. And the use of application domains would make a little bit more sense there. So we are adding some new functionality surrounding application domains. The first one is that we're adding some new APIs to the ICLR runtime host interface. And these are native application domain APIs. What they let you do is decide which application domain you're going to do a certain managed call in. So what you'll do is use the new hosting interface, the ICLR runtime host. That interface has always provided the ability to get your currently hosted CLR, enumerate your available app domains, invoke methods in the managed world, various things like that. But now you also get this function called execute in domain, where I choose the application domain that I want to do my execution in, and then I'll go and say I want to execute it in this application domain, I want to do this function. And from the native world, you don't always have to execute into your default app domain. The downside of this is that COM, which it uses, is a bit heavyweight for some of the scenarios. And it's certainly a bit messy to have to write that code where you do a core bind to runtime X because you actually have to get your running CLR instance to do these things. What we'll be doing in Whidbey is providing library support to make this very easy to do and very convenient. We'll have some templates where you can specify where your calls are going to take place from a native perspective in the managed world, and everything should look very clean. Unfortunately, we don't have those API shapes nailed down yet, so I don't have anything to demo, but I promise they will be neat, they will be very nice to use. Statics and globals are another big problem when it comes to application domains. If you've got global variables or static members of native types, pretty much anything with a static scoping in your native C++ code, in Visual Studio 2002 and 2003, these globals and statics are treated as process globals. They are specified in the image as an RVA. Now what this means is that they're shared across all of your app domains. So if you have a situation where you've got multiple app domains and you're loading up your mixed image into each of these app domains, and they're both trying to update this global or static data, they're actually stepping all over each other's data. So for example, if you're in ASP.NET and you're trying to leverage some of your existing C++ code from an ASP.NET page, and it's using the CRT, and maybe it's using stirtoke, for example, and somebody else loads up the same page, since stirtoke collects global data that is shared among everything in the process, they're both in the same process, and even though they're in different app domains, they'll be stepping all over each other. Now imagine how difficult this is to diagnose, especially in like an ASP.NET scenario. You don't own any code in that other app domain. It's somebody who's completely separate from you, who's just stepping all over your code, and it happens sometimes and it doesn't happen other times, and the real pattern is when the other guy happens to be using the machine. Very difficult to diagnose, definitely not the expected behavior in the managed world, because it violates this concept of app domains as isolated units of execution that we have. So we have some new features in Whidbey that address these problems. We're adding 2 new decal specs. First one is decal spec process, second one is decal spec app domain. Now, these parallel the use of decal spec thread that you use for saying that a particular statically scoped piece of data is going to be put in thread local storage rather than an RVA. So decal spec thread says TLS, decal spec process says RVA, decal spec app domain says you're putting it in per app domain storage. So the default is going to change to per app domain for both /CLR and /CLR pure. In /CLR safe, it doesn't make a difference because you can't use these statics and globals in /CLR safe. It's not verifiable. We believe this is the expected behavior because I think that as we move forward and folks are using app domains more often and they're using in the ways that they're intended to be used by the .NET architecture, it's just going to be way too confusing for the behavior to be where the globals are stepping on each other as they are now. It's definitely not the expected behavior. If you have come to rely on that behavior, you can continue to use it by using your decal spec process. So we have enabled the legacy case. The way we get this to work is that we've added a new concept to the CLI standard, and it's called a module constructor. And the way we did this, if folks are familiar with the way that types get initialized in .NET, there's what's called a class constructor or a CC-tor that gets put on each class, and that's guaranteed to run before you do any entry into something that is a member of that type or the type itself. So you can't access any data or run any code in that type until the CC-tor runs. What we've done is added to the standard a CC-tor for a module, so either for a .NET module or for an entire assembly. And that's guaranteed to run before any managed data or code is accessed in that module. So what we can do is every time that module gets reloaded into an app domain, we do all the appropriate initialization for the per app domain static in that CC-tor. So essentially now we have a managed entry point for DLLs and modules on the .NET frameworks. And we'll probably be leveraging that to greater effect later on. We've also got the native interface, which will be used for accessing per app domain statics, and we'll have library support for that. So if I've got some code that I'm not compiling /CLR that's just purely native, and for some reason or another I have to see one of these statics or globals that I've defined in something that's per app domain, I'll be able to use the libraries to say, I want to get access to this particular static or global in this particular app domain. So let's have a demo of those at work, and I'll show you pretty much the before and the after, where first we're stepping all over the statics and globals, and then we move on to a model where we're doing it on a per app domain basis. So I bring up the solution file for app domains. Now this is a bit of a complicated project, a solution rather, because I had to have multiple projects here. The reason for it is that you can't do an app domain execute assembly on something that's mixed. And since we definitely want to use mixed code for our app domain and process examples here, since we're doing process globals, I had to create these little shim loaders that were verifiable that went ahead and pulled in those DLLs. So what we do here in main, we first say we're doing per process, and then we use our process global loader and test that out. Then we do the same thing per app domain, and we use the per app domain loader. In each case, we create 3 app domains. We do an execute assembly on that app domain, and then we shut them down. Just for completeness, I'll show you what the loader looks like. All it is it's a class that on a thread starts up, figures out what app domain it's in, and just says, that global that you've exposed to me, I'm going to print it out, increment it by 1, and tell you what app domain I'm in. So here in our actual code, we've got a DeckelSpec app domain global with that getter and setter that I just referenced. And we've also got in the process case a DeckelSpec process getter and setter. So now if I do a build, everything builds successfully, and I do a run. We'll see these things come out per process in their polling. Now let me expand the size of this to make sure that everyone can see what's going on here. Oh, it decided to quit on me. Let me just add a... I'll add a read line in here. Rebuild. And then do my F5. So as this is polling, what's happening is in the first case, I've got these 3 threads that execute in turn. The first one will say, I'm app domain 1, I see 0, I increment by 1. The next app domain comes along, sees 1. It sees the increment that happened in the first app domain. The third app domain comes along, sees the previous 2 increments that have been done, does the same thing again, at which point app domain 1 comes back and sees 3. So each time here they're incrementing and every other app domain is seeing it. In the per app domain case, 1, 2, and 3 all see 0, regardless of the fact that every single one of them were incrementing. The next time they come along, they all see 1. Next time they come along, they all see 2, 3, 4, etc. So essentially, we've solved that per app domain problem by setting our defaults appropriately and giving you the power to toggle either way when you need to choose to go either per app domain storage or per process storage. So in summary, the main takeaway we're really trying to focus on here is that rewriting your existing C++ code is not necessary to make use of any .NET APIs, including WinFX. The C++ interop features offer the most flexible, most powerful, and in general best interop option for most users. But you do have to be aware of the transition costs when you're constructing these interop solutions because they can potentially bite you. Normally, you'll use the interop solution, and if you're seeing the performance problems, you'll go back and do some profiling, see where you're actually getting the interop penalties, and then move them either up or down the chain. Mixed DLL loading problem is fixed, but it's only fixed when Whidbey shifts. Before that, you still have to do the workaround. And if you don't do that workaround, there may be some issues later on with the CLR producing warnings when you're running it in debug mode, or even potentially having to change some configuration because those assemblies are not safe. Also, be mindful of app domains. If there's any possibility whatsoever that you'll be running in an app domain context, using the 2003 toolset, you have to be aware that your globals might be stepping on each other. I saw someone in the product pavilion the other day who's probably suffered from this exact problem. So if you're seeing strange behavior, this might be it. In Whidbey, We take care of a lot of it automatically, so you may not have to worry about it. Some additional resources. I gave a talk on Monday on targeting the CLR where I dive into the way that a lot of this is wired up from a technical perspective. You might want to check out the slide deck. We're pretty much done with the sessions for C++. I hope everyone's very excited about the technologies. We will be having a panel discussion on the future of .NET languages. That's on Thursday. It's at 1:45 p.m. There will be C++ representation, and if you've got any questions about the great C++ language innovations or what we're planning to do going forward, please attend the panel discussion. If you've got any questions or feedback, feel free to send it to me directly, to the VS-Wish alias, or on the public news groups. We've got Microsoft employees who watch those on a regular basis. Other resources, if you want to play with the Quake demo or even look at the source, it's at vertigosoftware.com/Quake. We've got our hands-on lab here at the PDC where you can go through a lot of these examples. We've got an Ask the Experts session that was yesterday, actually, so if you didn't go to it, sorry. And we've got the product booth in the product pavilion. So that's it. I'd like to take some questions now. Before everyone goes, please remember to fill out the feedback forms. They're using a new scoring system now. So if you thought the talk was really good, you give it a 9. If you didn't like the talk so much, you give it an 8. Yep.
I've got a question. Is this on? Oh, yeah, just.
Do you? Of the, were you, this is actually the last one. So whoever was the guy who I promised the T-shirt is the one who gets it. There you go. Question? Yeah. The question.
Should I come up or should I come? Okay. So can you compile any standard C++ with that CLR flag? Like, can you make complex types on the stack and other things you're not allowed to do in managed C++?
Yes, you can compile, except for some bugs which we don't plan to ship many of. Right. You can compile any standard C++ to MSIL.
Okay.
Yeah,
and if you want to see how that gets wired up, check out the TLS 401 slide deck. I go into detail on exactly how we do the code gen for those native types.
Okay.
For the mixed mode DLL loading problem in 2003, was that also an issue for mixed mode assemblies created in 2002?
Yes.
Okay, but the warning didn't show up until.
Warning didn't show up. We didn't discover it until a lot of teams within Microsoft started using the technology. And we've got, for one thing, we sign everything that we ship, and that creates some extra scenarios because when you're signing your code, you actually have to load up all those assemblies that examine the code security, right? And if you're doing that under loader lock, you've got some issues with more frequently running into that issue with the mixed DLL loading problem. Also, we've got some tools that we run on our code to put them under heavy stress, I/O stress and memory stress. And under stress conditions, the race tends to be lost more often.
Okay, you also mentioned that there were some possible configuration changes you could make that would help alleviate this problem if you were seeing it. I was just wondering if that kind of information is published somewhere.
We haven't decided exactly what our policy on unsafe DLLs is going to be yet. It was at one point discussed that we might even just generate an error with the CLR on any of those and say that they had to be reshipped. We backed off that because that's really just too aggressive of a user model. We're absolutely going to be doing something like when you're running a debug version of, if you're running the CLR in the debugger, and it happens to run into a case where you're trying to execute managed code under the loader lock, you'll get a warning and it'll tell you to fix it. Whether or not any of those warnings show up at runtime is policy that we haven't yet decided. But even if we do decide to create some sort of a warning situation in normal user runtime space, there'll be a configuration option to get around it so it'll be transparent to them.
Okay, thank you.
Sure.
Hi. You mentioned profiling. Other than finding p-invoke problems because that area of the code is slow, do you know of profiling tools that will specifically watch for p-invoke instances?
I don't believe there are any just yet.
Or is it possible with the monitoring APIs that are there to find that particular event?
You can certainly find the p-invoke statically with some of the tools that we have. As far as finding them at runtime and how often they get executed.
I want to find out where it's chatty, yeah.
Yeah, I'm not actually aware of any tools that are public right now that do that, but that situation will certainly change over time.
Okay.
Well, so if you're running Performance Monitor or pretty much any profile that supports mixed code, you're going to see the calls. But you don't have a category for a p-invoke transition. It could be other things going on inside the CLR. So it'll usually probably be the p-invoke. So it takes a little more work than we'd like right now to discover those issues, but we're working on solutions that'll make it easier to discuss it.
So there's some free samples I can download of how to use the low-level profiling APIs. But you're saying that particular event I couldn't look for, and even if I wrote my own tool.
If you're using the low-level profiling APIs, definitely you can find it. Yeah.
Okay, so they're in there. Thank you.
Yeah. Sorry.
So if you take native DLLs, let's say you're calling through interop from wrappers and exposing, let's say, in regular .NET, however you do it.
Yeah.
So you decide to take some of these DLLs and build them with /CLR.
Mm-hmm.
You're going to be creating a separate assembly for each DLL?
So every DLL that you used to have a native binary for, you'll now have a DLL which has MSIL implementation.
Right, but is that an assembly?
It is an assembly. All an assembly is a portable executable file,
right.
The same thing that we generate native code for with some extra information stuck in it.
Okay, so now when you had these separate DLLs with their own interfaces, now those DLLs now are public metadata that everyone can...
So there is metadata there?
Yeah.
Has anyone ever ILDASM'd it?
Yeah.
So you can tell me how readable that is.
Uh-huh. Okay.
There is metadata there, but whether or not there are IP concerns is...
No, but I'm just trying to understand, that's what you'll end up with.
That's what
those
you'll
will
end
all
up
be
with.
separate assemblies with all that.
Yeah, and the metadata is name mangled. It's not very
Oh, yeah.
pretty. It's the type of stuff we have to do in order to get it working. There are also, if there are concerns about exposing some of your method names, there are obfuscators that work on mixed images. Dotfuscator, for example, which we ship with the product, does work on mixed images, and it'll crack the binary and do the appropriate changes to the method calls.
And so there are things like, signing those assemblies, putting them in the GAC, and issues that you'd have?
Sure, you can.
So you can put that on those assemblies just like any other?
Yep.
Okay.
And a lot of the assemblies that are shipped by the CLR team are mixed assemblies.
Mm-hmm. Okay.
Any other questions? Thanks for coming out.